So good morning all of you. So in this chapter we will be discussing the mathematics of cryptography part 2, and we will be mainly discussing various types of algebraic structures that are commonly used in cryptographic algorithms. So these are the objectives of this chapter. We will be seeing three types of algebraic structure. The first are the groups, then rings, and the third is the fields. Apart from them, we will be also discussing the finite fields of type GF2 to the power n. Using this finite field, we can perform operations like addition, subtraction, multiplication, and division on n-bit words in modern block ciphers. So as you know that cryptography requires a set of integers and the specific operations and that are defined on those sets. So till now we have studied different types of sets like Z, Zn, Zn star, Zp and Zp star, etc. So the combination of the set and the operations that are applied on the elements, so that entire things forms an algebraic structure. So as I have told, in this chapter we will be seeing three common algebraic structure, that is groups, rings and fields. So first we'll see groups, then second we will see rings, and the third we will see fields. So a group is generally denoted by G, is a set of elements with a binary operation denoted by dot, and which satisfy four types of properties. So apart from them, a group can also satisfy the fifth property, that is the commutative property. So let us see these properties one by one. The first property is the closure property. So the closure property states that if suppose we have two elements A comma B and both of them belongs to group G, then the result of performing A dot B, so that element C which is obtained by performing A dot B, that element C should also belong to G. So this is known as the closure property. Second is the associative property. So associative property states that suppose we have three elements like A, B and C that all belongs to this group G, then the associative property states that A dot B dot C is equal to A dot B dot C. So in other words, we can say that it does not matter in which order we apply the operation on the two or more elements, the result will be same. Third is the commutative property. So again, let us assume that there are two elements, say A and B, that belongs to G. Then commutative property states that A dot B should be equal to B dot A. So if this property is satisfied, we say that the group is commutative, and commutative group, or it is sometimes is also known as abelian group. So a commutative group is also known as the abelian group. Then the fourth property is the existence of an identity. So for all the elements, A that belongs to G, we have an identity element that is denoted as E, and that for that identity element A dot E is equal to E dot A equal to A. So whenever we perform this dot operation with this identity element, then the result will be the original element itself. And finally, the existence of inverse. So there will exist an element, we will denote it as A prime, and the property is that whenever we perform this operation A dot A prime, this is equal to A prime dot A, and this is equal to your identity element. So whenever an element is this operation is performed with its inverse, then we will get the identity element. So these are the five properties which a group satisfy, and if in fact there are four properties, the fifth property is the commutative. So if the group also satisfy the commutative property, we say that it is an abelian group. So here we have shown all these five properties, and again the point to be noted that the third property needs to be satisfied only for the commutative group. Now where is the application area of these groups? So although this groups involves a single operation, but the properties imposed on the operation allow us to use a pair of operation as long they are inverses of each other. So let us suppose that we have a pair of operation like addition and subtraction. So since they are opposite of each other, so we can apply both of these operations on a group. For example, suppose we have a set of residue integers with the operation addition operator. So this Zn and this Zn denotes the set of residue integers, and we have an operation plus, that is the addition operator. So it is a commutative group. We can see that this group satisfy all the 5 properties that we have just discussed, and apart from them we can perform both addition and subtraction on the elements of this set without moving out of the set. So it means that both the operations are possible at the same time. So some more examples about this group. So suppose we have the set Zn star with the multiplication operator. So this is the group set of elements with Zn star, and we have this operator that is the multiplication operator. So it also satisfies all the 5 properties, and that is why it is an abelian group. So you can check manually that whether all the 5 properties are satisfied or not, and you will find that yes, it is an abelian group. And not only such kind of sets like Z or Zn star can make a group. In fact, we can also define a group with an elements like these A, B and C, D. So suppose we have a group with the 4 elements A, B, C and D, and this is the operation dot. So this kind of set can also form a group as shown in this table. So as you can see that we can, whenever we perform any operation between the 2 elements, the result is within the group itself. So that is why the closure property is satisfied. Second property, if you can see that that is the property of associativity. So suppose if I performed this operation A plus B plus C, so the result of this operation, you can verify that A, you can say plus or you can say dot, that does not matter too much. So let me change it to A dot. So A dot B dot C. So first we will check what is A, result of A dot B is B dot C, and the result of B dot C is D. Okay, and then suppose if I compute A dot B dot C, so this will be equal to B dot C is D, and A dot D is D. So it means that the commutative properties, the associative property is satisfied. Then if we check the commutative property, so you can find that A dot B is equal to B dot A for all the any pair of elements among A, B, C, D. You will find that this property is satisfied. And then the identity element. So the identity element, as you can see that A is the identity element, and if we need to find out the inverse, so the inverse are pair of inverse are A comma A, they form one pair of inverse, then B comma D, they forms a pair of inverse, and then C makes a inverse is C. So all the elements have their inverses, so it means that this is a abelian group. Apart from them, there is a very interesting set of group known as the permutation group. So the set is the set of all the permutations, and the operation is the composition. So if you remember from our last lecture, that permutation basically means that we are rearranging the elements in some other order, and in case of permutation group, the operation is basically composition. Composition means that one permutation, first we apply first permutation and then we apply the second permutation. So the combination of or the composition of these two permutation is basically the operation. So Now you can see that the results of these two permutation 312 and 132, this is equivalent to the permutation applied in this order 3 to 1. So this property has a very important effect for the cryptographic algorithm. So apart from this, let us first see that it satisfies all the properties, such a composition operation that satisfy the closure property. Associative property is also defined. Commutative property is not satisfied, that you can check. The commutative property is not satisfied, and all this set has an identity element, which means that there will be no permutations, and each of the element has an inverse also. So that inverse can be found using the identity element. So in this manner, this permutation group is defined. So this is one of the example of a permutation group defined over a set of elements. So this group has been defined over the set of elements 1, 2 and 3. So since there are 3 elements, so the possible number of permutations are 3 factorial, that is 6 different types of permutations can be found, which are shown in this table. And as you can see that the identity element is 1, 2, 3, and this permutation is the identity element. So as you have seen that we have shown that the set of permutation with the composition operation, it forms a group. So this implies that using 2 permutations one after another cannot strain the security of the cipher, because we can always find a permutation that can do the same jobs because of the closure property. So it does not make any sense to perform again and again different types of permutation, because there is always a possibility to find a single permutation which has the same effect as performing n different permutations. So this shows that applying different permutations in a cryptographic algorithm will not increase the strength of that algorithm. Next, a few more definitions, like the finite group. So a group is called a finite group if the set has the finite number of elements, otherwise it is an infinite group. So the number of elements that denotes the denotes the order of the group, and if the order of the group is finite, then it is a finite group, otherwise it is a infinite group. Then there is also a term that subgroups, which is an important term. So a subset H of a group G is a subgroup of G if H itself is a group with respect to the operations on G. So suppose we have a group G, and from this group G we have taken a subgroup, that is G H. So let me show you the notations here. So suppose we have a group G that is defined as S comma dot operation, and from this subgroup we have from this group we have a subgroup H, which contains the set of elements T, and it works with the same operations dot. Then it will also this also a group, it satisfies all the 4 properties, so then it is also a subgroup. So let us see some examples here. So if I ask that whether the subgroup H of Z10 plus is a subgroup, so yes, it is a subgroup of Z12. So we will say no, it is not a subgroup. Why? Because this Z10, this works with modulo 10 operation, while this Z12 works with modulo 12 operation. So that is why H is not a subgroup of G. Next are the cyclic groups. So if a subgroup of a group can be generated using the power of an element, then the subgroup is called a cyclic group or cyclic subgroup. So suppose we have a element A of that subgroup. So suppose we have an element A that belongs to that subgroup H, and all the elements of this H, if they can be generated by the powers of n, a to the power n, so then we say that that subgroup is a cyclic subgroup. So let us see with an example. So suppose we have the group G defined as Z6 and with the operation addition. So Z6 means that it contains these elements 0, 1, 2, 3, 4 and 5. So in order to find out which subgroups are the cyclic subgroups, so we'll start one by one. We'll start with 0. So as you can see that 0 raised to the power n mod 6 is 0, so that it means that 0 can generate only one element, that is 0. So the first subgroup we'll say H1, and it contains the element only 0 over the operation plus. Then we will start with 1 and see what are the different elements it can generate. So 1 to the power 0 mod 6 is 0, 1 to the power 1 mod 6 is 1, and if I continue in this manner, we will find that 1 is able to generate all the elements of G. So we will say that this subgroup, say it is denoted by H4, so that will be equal to G. Then we will check for 2, so this 2 is able to generate 3 elements, that is 0, 2 and 4. So this let us denote this by H2, and it can generate only 3 elements, 0, 2 and 4 over the operation plus. Then 3 can generate only 2 elements, 0 and 3, so it will form another subgroup. Say it is denoted by H3 and it contains 2 elements, 0, 3 and plus. Similarly, if we see 4, then it generates the same element generated by 2, so 0, 4 and 2. So these are two same, this one and this one, they are equal. So again we will denote this subgroup by H4, that is equal to G. And if we see 5, so this 5 is able to generate again all the elements 1, 2, 3, 4, 5 and 0 itself. So this would be equal to the group G itself. So in this manner we can find out what is the generator element, and that generator element is able to generate which elements. So then we will find out what are the cyclic groups. One more example. So suppose we have the set Z10 star. So Z10 stars means all the numbers which are relatively prime to Z10. So the Z10 star basically contains 4 elements. So 1, 3, 7, 9, all the elements which are less than 10, that is they lie between 0 to 9, and they should be relatively prime to 10. So there are only 4 numbers, 1, 3, 7 and 9. And if one by one we will find the what elements they can generate. So 1 can generate only 1, 3 can generate all the 4 elements, 1, 3, 9 and 7. 7 can again generate all the 4 elements, 1, 3, 9 and 7, and the 9 can generate only 2 elements, 1 and 9. So mainly there are 3 subgroups, so that this will be called as H1, and this we can denote it by H2, and both of them, this H3 and H3. So in this manner we can find out the cyclic subgroups for this group G. Similarly, we can have a cyclic group. So a cyclic group is a group that is its own cyclic subgroup. So that we will say that it is a cyclic group. So for example, if we say let us see some examples. So just now we have seen for Z10 star for the operation multiply, we have G has, in that case G has 4 elements, 1, 3, 7, 9, and there were 3 cyclic subgroups, H1 which contains only 1, H2 which contains 1, 9, and there was a cyclic subgroup H3 equal to G. So it means that this H3 is will make a cyclic group. Then for the group Z6 and plus, the cyclic groups are generated by the generator 1 and 5, and for the cyclic group Z10 star, that is generated by 3 and 7. These are the two generators. So why they are called as generator? Because using these elements we can generate the rest of the elements, so they are known as the generator elements. Now there is a Lagrange's theorem related to these cyclic subgroups. So assume that G is a group and H is its subgroup. If the order of G and H, that is this value, and this value denoted by G and H respectively, and then based on the theorem H divides G. So if H is a subgroup of G, then the order of H will divide the order of G. And what is the order of an element? So the order of an element is the order of the cyclic group it generates. So the order of that element is the number of elements that are present in its corresponding cyclic group. So these are some confusing terms. You have to go through it, you have to practice it so that you can remember what is a group, what is a cyclic group, what is the order of a group, what is the order of a cyclic group, and order of the element. So these are very similar type of terms, but you have to remember, you have to take care when we are talking about order of the group, and in what case we are talking about the order of the element. So the order of the element is the order of the group, cyclic group, that it generates. So for example, we have the group Z6 or defined over addition operation. So this is our group, and if we find out the order of the elements are, we will find that since 0 generate only one element, so the order of 0 is 1. 1 can generate all the elements in this, so order of 1 is 6. 2 can generate only 3 elements, so order of 2 is 3, and so on. Similarly, we can find the order of elements in Z10 star. So this Z10 star that contains only 4 elements, that is 1, 3, 7 and 9, and the number of elements they can generate, that is equal to their order. So order of 1 is 1, order of 3 is 4, order of 7 is 4, and order of 9 is 2. So that you can go back and see the previous example how these elements were generated. So you need to generate those elements, and then based on their count you will define the order of that element. So this completes the first algebraic structure, that is the groups. Next algebraic structure is the ring. So a ring is again defined over some set of elements with two operations, say dot and say some other element, say square, or we can denote it by plus or any other symbol also. So basically there are two operations. Then corresponding to the first operation, all the 5 properties should be satisfied. So that is the closure property, that the first operation should satisfy the closure property, associative property, commutative, existence of identity, and existence of inverse. But for the second element, 3 properties, or in fact 2 properties needs to be satisfied, the closure property and the associative property. And if suppose the second operation also satisfies the commutative property, then we will say that this ring is a commutative ring. Okay, so I hope this part is clear. There are 2 operations for the ring, say dot and you can say the square operation. So this dot operation, they satisfy all the 5 properties, while the other operation, the second operation, will at least it should satisfy the 2 properties, that is closure and associativity, and if it satisfy the commutative property also, then we will say that it is a commutative ring. So for example, the set Z with 2 operation, addition and multiplication, is a commutative ring, that we can show it easily that addition satisfy all the 5 properties and multiplication satisfy only 3 properties. So that is why this will make a ring. And then we have the third type of algebraic structure, that is field. So a field is denoted by, again, same types of notation is there. We have some set of elements. These are the set of elements, and we have two operations. So this operation is not visible here. So we have two operations, first operation and the second operation. And a field is a commutative ring in which the second operation satisfy all the 5 properties. So we have seen what are the properties satisfy a ring. So field is also a ring, but in this case the second operation, it satisfies all the 5 properties defined for the first operation, except that the identity of the first operation has no inverse. So as you can see that for the first operation all the 5 properties are satisfied. So these are 5 properties are satisfied for the first operation, and for the second operation these 4 properties, at least these properties should be satisfied, and for the fifth property, that is the existence of inverse. So the identity element of the first operation has no inverse with respect to the second operation. So let us see some more about fields now, the different types of fields that are available. The first is the finite field. So Galois showed that for a field to be finite, the number of elements should be p to the power n, where p is prime and n is a positive integer. So finite means that it should contain finite number of elements, and that finite number of elements should be p raised to the power n, where p is a prime number and n is a positive integer. So if this property is satisfied, then we say that it is a finite field. So when n is equal to 1, in that case we have the Galois field p, then it will also be a field, and this field can be set to zp. So since we know that p is a prime, so we can denote the set of elements as zp, which will contain all the elements from 0 to p minus 1, and there will be 2 types of arithmetic operations, say addition and subtraction or multiplication and divisions. So based on those operations we can define a Galois field over p. So one of the common example of this finite field is GF2. So this GF2 it contains 2 elements, 0 and 1, and there are 2 operations which have been defined, that is the addition operation and the multiplication operation. So 2 operations have been defined. These are the set of elements, and these are the 2 operations that have been defined, and we can see from this table how these operations can be performed. So 0 plus is 0, 0 plus 1 is 1, then 1 plus 0 is 1, 1 plus 1 is 0. Similarly for the multiplication of operation, this is just like your normal mathematics. Anything multiplied by 0 will give 0, 0, and when anything is multiplied by 1, it gives the same number itself. And then we have this is the for identity element and the inverse element. So for any number a, these are the inverses. So if a is 0, then the inverse will be 1, additive inverse, and if a is 1, then it inverse will be 0. And for the multiplicative inverses, if the number is 0, then this inverse is undefined, and if the number is 1, then its multiplicative inverse is also 1. So in this manner we can compute the operations, and we can also calculate the inverses for finite field GF2. Similarly, we can define the finite field GF5 where 5 is a prime number, and there are again 2 operations, addition and multiplications. So we have these are the set of elements 0 to 4, and we have 2 operations, plus and multiply, and we have defined the tables for addition and multiplications. And here on the right side we have shown the additive inverse and the multiplicative inverse, so that you can see and that you can again compute it by yourself also how these values are obtained. So just to summarize, that there are three types of algebraic structure: groups, rings and fields, and the different operations that are supported are plus, minus and multiplication and divide in case of groups. For the ring, only this operation is defined, plus and minus and star, the multiplication. And for the fields, all the four operations are supported: addition, subtraction, multiplication and division. And on the third column we have shown the supported type of set of integers. So the group supports both Zn and Zn star, ring supports Z, and the field supports the Zp, where P is a prime number. So the next, the very important type of the fields of the finite field is GF 2 to the power n. So in cryptography we often need to use four operations, that is the addition, subtraction, multiplication and division. So we can say that, in other words, we have to use fields whenever we say or whenever we talk about these four operations. So what we can do, we will use GF 2 to the power n and with a set of 2 to the power elements, and these elements are basically the set of n bit words. So we'll see how this n bit words are defined. So first let us see what are the polynomials, then how to use a generator for generating these 2 to the power n group field. So let us take an example. Let us define GF 2 to the power 2, where n is equal to 2, and it is a field in which the set has 4 2-bit words. So the 2-bit words are 0 0, 0 1, 1 0 and 1 1. So these are the 4 2-bit words, and we can accordingly redefine the addition and subtraction on this set in such a way that all the properties of these operations are satisfied. So here, as you can see on the bottom, that there are the operations defined for addition and multiplications. So they are defined in such a manner that all the properties are satisfied. For this, in case of addition, the identity element is 0 0, and in case of multiplication, the identity element is 0 1. Then next is the polynomial. So these polynomials are defined just like in your normal mathematics. So a polynomial of degree n minus 1 is an expression of the form. So this is your coefficient an minus 1, an minus 2 up to a1 and a0, and these are all coefficient, and x is the value to which the power of n is defined. So we have x to the power n minus 1, x to the power n minus 2 up to x to the power 0. So here xi is called the ith term and ai are known as the coefficient of the ith term. So in this manner we can define the polynomial fx. Now how we can represent a 8-bit word using this polynomial? So the representation is very easy. Suppose we have a 8-bit word like this, 1 0 0 1 1 0 0 1. This is our 8-bit word, suppose. So corresponding to the positions where we have the bit value 1, we will set the coefficient as 1. So in this case the coefficient is 1, here the coefficient is 1, here also, and here. So all this position we will set the coefficient as 1, and on the remaining position we will set the coefficient as 0, and then we will assign the powers of x starting from x to the power 7 to at the end x to the power 0. So first we will simplify it. We will get this 1x to the power 7 plus 1x to the power 4 plus 1x cube plus 1x to the power 0, and then we can further simplify it and get the polynomial as x to the power 7 plus x to the power 4 plus x cube plus 1. So that will be the representation for our 8-bit word. Okay. Then in order to find the 8-bit word related to a polynomial x5, x to the power 5 plus x square plus x, so that can again be done very easily. What we need to do, we need to write all the powers of x starting from x to the power 7 to x to the power 0. Then we will see that the coefficients are 1 for x to the power 5 x square and x, so we will write the coefficients for them as 1 here, 1 here and 1 here, and rest of the coefficients we will put at 0, and in this manner we will get our final 8-bit word as 00, 100 and 110. This is our 8-bit word. So just we have to reverse the process to get the 8-bit word. Now whenever we are talking about polynomials representing 8-bit words, then we have to use two types of finite fields. First is GF2 and as well as GF2 to the power n. So let us see how we can use them. So for the set of polynomials in GF to the power n, a group of polynomials of degree n is defined as the modulus, and such polynomials are referred to as irreducible polynomials. So for all the polynomials that are in GF to the power n, we will define an irreducible polynomial, or sometimes it is also known as the prime polynomial. So it is also sometimes known as the prime polynomial. Why prime polynomials? Because they cannot be further factored into some other smaller polynomials. So for example, for the degree 1 we have two irreducible polynomials, that is x plus 1 and x. These are the two irreducible polynomials, also known as the modulus. Similarly, for 2 we have defined this kind of prime polynomial. For 3, 4 and 5 and so on, we can define corresponding to each degree, we can define a irreducible polynomials, and this polynomial will help us to keep the operations of multiplication whenever we are multiplying two polynomials together. So by using these irreducible polynomials or the modulus, we can again bring the results within that GF to the power n itself. So we'll see that now how the addition and subtraction operation and along with multiplication and division operation. So addition and subtraction operation are the same as we do it on normal polynomials. For example, suppose we need to add two polynomials, x to the power 5 plus x square plus x and x cube plus x square plus 1 in GF2 to the power 8. So we need to add these two polynomials, and this symbol is the polynomial addition. This symbol is used to show that it is a polynomial addition. So simply we need to write these polynomials in two rows. So we will write these polynomials in two rows, the first polynomial and then the second polynomial. We will add the coefficients, and then finally we will get this result, that is x5 x plus x cube plus x plus 1. So that is very easy, that you have done in your normal mathematics. In that exactly in the same manner we can perform addition and subtraction. In fact, the result of addition and subtraction is same, and these results can be obtained by taking the XOR of the coefficients at the same position. So this is basically a shortcut because the addition of in GF2 means the exclusive OR operation. So we can XOR the two words bits by bits to get the result. So simply by doing XOR we can get the addition of two polynomials or the difference of two polynomials. Next comes the multiplication, how we can perform the multiplication for the polynomials in GF2 to the power n. So the coefficient multiplication is done in GF2, and by multiplying two coefficients or the two powers x ki power I by x ki power j, we will get the result as x to the power I plus j. Okay, but there is a catch, that the multiplication may create terms with degree more than n minus 1. So that can be quite obvious, that when we are multiplying this x to the power I and x to the power j, so this I plus j, that is greater than n minus 1. So which means that the results needs to be reduced using the modulus operator. So now the modulus polynomial will come into play, how it can be utilized to reduce the result again back to maximum to the power n minus 1. So let us try to see the multiplication of these two polynomials. So suppose we have a first polynomial, and this is p1, and this is the polynomial p2, and we are multiplying both of these polynomial in group Galois field 2 to the power 8. So again the process will be same. First x to the power 5, this x to the power 5 is multiplied with p2, then this x square will be multiplied by p2, and then finally x will be multiplied by p2. So one by one we'll multiply, and then we will perform the simplification, and finally we will get the result like this: x12 plus x7 plus x square. But since all these operations, all this result should also belong to Galois field 2 to the power 8, so we need to perform the reduction, and this reduction is performed with the help of the modulus. So this modulus, or the reducible polynomial, will be given to you in the problem itself. So for example, in this case, the reducible polynomial is this, has been given within the question itself. So we have to divide it with this irreducible polynomial to get the result. So how this division will take place? So let me show you the process of division. So let me show you the process of division. So this division can be done like this. So we have the irreducible polynomial, that is x to the power 8 plus x to the power 4 plus x cube plus 1, and we need to reduce the polynomial x to the power 12 plus x to the power 7 plus x square. So just like we do the division, in the same manner we will check that here we have 8 and here we have 12. So we will multiply with x to the power 4, and we will get x to the power 12 plus x to the power 8 plus x to the power 7 plus in fact there is one more term x here, x to the power 5 plus x to the power 4. Okay, then we will perform subtraction, or you can simply do the addition. These are both same. So we will get x to the power 8 plus x to the power 7 plus, sorry, x to the power 7 will not be there, it will cancel out. So x to the power 5 plus x to the power 4 plus x square. Then we will see that x to the power 8 and x to the power 8, so since they are both same, so we will multiply by 1. So we will get x to the power 8 plus x to the power 4 plus x cube plus x plus 1. Again perform addition or subtraction, so we will get x to the power 5 plus x cube plus x square plus x plus 1. So this will be our final result. This will be the result of multiplication of the two polynomials p1 cross p2. So in this manner we have to reduce the result and get the actual result, which will belong to gf to the power 2 to the power 8. Okay, so I hope this division process is clear to everyone. In the same manner we can compute the inverse. So suppose we have gf 2 to the power 4, and we have to find the inverse of x square plus 1, and the modulus or the irreducible polynomial given is x to the power 4 plus x plus 1. So we can apply the your Euclidean algorithm to calculate the inverse. So again we will form the table like this. So the first column is q, the quotient, then we will initialize r1 and r2. So this will become your r1 and this will become r2. So we'll divide r1 by r2, and we will get some quotient here, and then we will get a remainder also. And then there are two more variables, t1 and t2. They are initialized with 0 and 1, and then based on that extended the Euclidean algorithm, we will calculate the value of t. So one by one we will repeat this process until this r2 becomes 0. So once it becomes 0, then the inverse is x cube plus x plus 1. This is the inverse. So in this manner you can compute the inverses on polynomials also. Similarly, one more example, we need to find the inverse of x to the power 5 and with the given modulo polynomial. So again we can apply the Euclidean algorithm. The process will be same. Again we need to construct the same type of table, and once when r2 becomes 0, we will get the inverse as x to the power 5 plus x4 plus x cube plus x. That is the inverse. So in this manner you can compute the inverse. So to summarize, the finite field gf to the power n, and this can be used to define 4 types of operation, that is addition, subtraction, multiplication and division over n bit words, and the only restriction is that division by 0 is not defined. So this completes this unit about the algebraic structures. So we have seen 4 types of algebraic structures: groups, rings, fields, and your finite fields, that is defined as gf2 to the power n. And we have seen the properties that are satisfied by these algebraic structure over a set of operations. And hopefully this topic is clear to everyone. If you are having still if you have any doubt, you can discuss with me in the discussion session which is on Saturday. So feel free to contact me and we will discuss there. Okay then, thank you.